geometry, calculus, complex analysis. All these three subjects combined into the final challenge. That final challenge is... Fourier analysis. I guess that makes sense.
Isn't that the thing that can turn any shape into a series of circles?
It is, but it has a lot more use cases than that. So, let's begin. For the actual last time of this year, this is Summer of Math Exposition, or... Now, to explain what a Fourier transform is, we first have to explain what a Fourier series is. First of all, you said that we can create any shape out of circles, right?
Yeah.
Well, let's answer a simpler question. Can we create any wave using just a sum of sine and cosine functions?
How is this related to... Oh yeah, because if we treat the shape as parameterized on t, and if it's closed, then the x value loops up on itself, and the y does also.
For example, the x-coordinate of these two lines forms what's known as a square wave. You can see why it's called that.
So, how do we turn this square wave into a bunch of sine waves? Sine waves are smooth. This is straight.
Well, for convenience, let's say that the amplitude is 1 and the period is 2 pi.
Just like a regular sine wave. In fact, I think we can fit a sine wave here. But this still isn't a square wave.
So, we add another sine wave.
Well, adding a sine wave with the same period only increases the amplitude. So, we increase the period by say 2? No, 3 works better.
The correct period, of course, is 3. Remember, we're adding to the sine wave, so we need to make sure we don't go overboard. So, how about a third sine 3x?
So, I'm guessing that the pattern continues? The next term is 1 over 5 sine 5x, right?
Yeah. Wait, why are we saying x? We should be saying theta.
Oh yeah.
So this is the completed series, and to show that this is actually equal to the square wave, here's a visualization.
You can see that the point stays at the top half for a while before quickly moving down to the bottom half. Just like a square wave.
Of course, we don't have to use the square wave. This is the Fourier series of the saw wave. The wave determined by the x-coordinate of a parameterized version of a crescent shape. Here's its Fourier series.
Just don't look at what happens when you plot its epicycles. It gets the value of x correct, but y, not so much. But we'll fix that later.
For now though, we can see that every variable that repeats itself over time can be expressed as sine waves.
Like the sound wave for my guitar.
But then we went to a problem. How are we supposed to find the coefficients for the Fourier series? Of course, we could do trial and error, but ain't nobody got time for that. Introducing the Fourier transform. Say that the function f is defined in an interval I with length p. To find the coefficients of its Fourier series, use this formula.
Looks difficult.
Don't worry, if you remember, e to the I theta is equal to cos theta plus I sine theta, so we can substitute that in. And since we're dealing with real valued functions here, for now that is, let's remove the I from the sine term. This is done without loss of generality, of course.
Because it's the same as multiplying the last constant by I, right?
Exactly. Let's plug in the square wave here. For values between 0 and pi, the square wave equals 1, and for values between pi and 2 pi, the square wave equals -1. So we put that in. Now, since the integral of cos is sine, we get this. However, sine of pi times any integer is 0, so this whole thing is 0.
However, if you do the same thing with sine, you actually get something. Since cos of 0 and cos 2 and pi are both equals 1, and cos of pi n equals -1 for odd integers and 1 for even integers, you get an oscillating thing. This is 4 over n pi for odd integers and 0 for even integers, exactly the same as the series we found before, just stretched out.
Side note, if I add the entire number line, then the formula changes is to the one we saw in the beginning. An intuitive explanation as to why this works is as follows. For each x, if both the function and the wave is positive at that point, or both negative, then the product is positive. If one is positive and the other is negative, then the product is negative. If we sum up all these individual values, if the total area is positive, then the wave is overall correlated. If the area is negative, then its inverse will be positive, and if it's zero, then it isn't correlated at all.
I've also seen this explained with polar coordinates. You should watch Brew Brown's video for a better explanation, and it has a much cooler visual proof to go with it.
The Fourier transform is a very useful thing to have around. In general, whenever there's a wave, the Fourier transform appears, acoustics and quantum physics for example. However, the most popular use of these is, like Sayo said, to make shapes with spinning circles, epicycles if you will. However, the output of a Fourier series is only one-dimensional, and we need two dimensions. If only there was a way to get two real numbers in one value. Oh yeah, that's right, complex numbers.
The Fourier transform already has a complex number in it, so it works out.
Yes, first, draw your shape in the complex plane, then parameterize it. Here's the parameterization for the crescent shape. Let's bring back the complex form of the Fourier transform. In sorting our function, we can split it up into 3 different integrals, which we can make 4 to make our lives easier.
Since these are exponentials, they are easy to integrate.
Solving these integrals, we end up with this. Please note that the terms at 0 and 2 pi have cancelled out.
We can also cancel out the i's and negative i's here and here, making sure to switch the sign for when it's a negative I.
Now, do you notice anything?
You can pair up each term. Therefore, you can rewrite this whole thing like this.
Also, since 1 over I equals negative I, we can turn these into these. Now, negative I to the n plus I to the n is equal to this, which is just equal to 2 cos I over 2n.
I think I see where to go now. When n is odd, then the cosine is 0, and when it is even, it alternates between 1 and negative 1. Therefore, we can rewrite this as this.
Also, when n is equal to 1 or negative 1, it's equal to 0 over 0. These are the values at C1 and C negative 1.
Did you say negative 1?
Yeah, in the complex form of the Fourier series, n actually goes in both directions. Anyway, here's our completed formula.
Looks very similar to when we're just considering one coordinate.
Pretty much all we did was add a term of I sine thing, but it makes all the difference, as you can see.
Wait, what's that bright light?
The mathematical object is transforming!